morning, everyone. Well, it's a great pleasure to introduce Dr. Stephan Preibisch. Dr. Stephan Preibisch is Director of the Scientific Computing Software at Howard Hughes Medical Institute, and he basically specializes in petabyte scale data for electron microscopy and optical microscopy. Over the years, when he was group leader in Berlin, he developed several open source tools, software for light sheet microscopy, spatial transcriptomics, machine learning, and other things that he shared for the community. Now he's leader, co-founded of the Shanilia Open Science Software Initiative, and has contributed with several, software tools like Fishy Image Lib 2, Big Data Viewer, Big Stitcher, Spatial Transcriptomics, and so on. When we discuss with Stephan about his presentation today, we asked him particularly to share his experience in setting up one of the world-class data centers and software groups for problems that are out of the scale that we can think even about. But we wanted to have basically as a north for our discussion, which is something that as a lobby are facing in the future, and we wanted to think collectively how we can achieve such a thing, which is very ambitious, but for sure, as usual, if we collaborate and we think together on how to establish these resources in the region, we can achieve something that can be impactful and long-lasting. Thank you very much, Stephan. I think you are remotely. I have to say that unfortunately he couldn't be here because the problems with flights, but he was very neat to come over and spend time and share discussion with us. So most probably in the next opportunity we will have you here, Stephan.
I think this was considered a big problem. We were at around half a gigabyte of data. A few years later, we wrote software for reconstructing cleared and expanded samples in the size of around a few terabytes. So here you see the mouse, and here you see a Drosophila installable brain again. And these days we're entering the petabyte range. We're not yet there, but the acquisitions are clearly going this direction. What you see here in the background is a light sheet acquisition of a 3 times expanded mouse brain created by the Allen Institute. Adam Glaser is the one who built the access per microscope to acquire those images, and we're going to talk about this more. At Genea, we're also going this direction. Philip Keller built a new scope together with Mo Tabakodi. We're now expanding tissues 16-fold. This is Drosophila and mouse cortex to a degree that hopefully allows us to do connectomics with this in the future. So we're really scaling up towards the petabyte scale. And with that, we're actually going into a territory where usually electron microscopy was the method of choice. Right, so what you see, the video you see in the background, I hope displays somehow reasonably across the connection. It's a reconstruction of almost a petabyte of data of a Drosophila central nervous system, so brain and VNC. And you can really follow every single neuron throughout the entire brain, seeing what is connected to what, as illustrated by this illustration that was made. So these are the two technologies that we are actively developing and pushing forward, and that we have been developing software for. So now the cool thing is, with light sheet microscopy, as I said, we're finally going into the domain where we can actually do the same thing with light microscopy, tracing individual neurons, which is, I think, a pretty interesting direction. And I wanted to mention this because this is actually what drives us right now to develop all of this technology that I'm going to talk about. If there are any questions in between, please feel free to interrupt me or ask something that's of course fine. So as I said, the microscopy and sample prep made amazing strides forward over the last years. I mean, this is really, the last 20 years are kind of remarkable in that sense. And at the same time, software, data, and collaboration had to catch up with this in order to make sense of these fire hose of data, as Harold Hess always calls these new types of microscopes. And what I want to do is I want to tell you the two stories a little bit for inspiration, how we reconstruct data for light sheet and how we reconstruct data for EM. So light sheet microscopy, what you see here on the right is the classical drawing of a light sheet microscope from 2004 from the Stelzer lab. You have the sample in the middle somehow hanging or being on a stage. You have a light sheet and you have an objective that is arranged perpendicular to it. You can move your sample through the light sheet and create a three-dimensional stack of your acquisition. In the beginning, this microscope was mostly used for live acquisitions, like looking at the developing Drosophila embryo. These days, the number one application is tiled acquisitions of ever-increasing in size acquisitions of mouse, Drosophila, and what have you. What I wanted to show you is how we developed the software to work with this type of data using the collaboration with the Allen, where Adam Glaser built this new type of light sheet microscope, the ExaSPIM, where they used meteorology lenses and other really cool improvements to build a microscope that can image gigantic volumes with just a few tiles. So each of those images of this mouse brain, for example, is 15,000 by 10,000 by 30,000 pixels, more or less. So these are gigantic image tiles using these sensors that are, again, not from biology. And this is how all of this started, right? So this is how the collaborative development of software basically took its course. Before I tell you a bit more about how we did this, I want to tell you what the basic problem is that we're solving, or the first step, what the reconstruction of the sample actually means. So you have this overlapping set of images, as you can see here. And the microscopic stage tells you that's more or less how they are arranged in 3D space. That's how they actually are arranged in 3D space for tons of reasons that I will not go into detail, but we can discuss this, of course. And what's actually happening, they're actually also a bit deformed for various reasons, like sample-induced light aberrations, etc. How we solve this in general is that we find pairwise overlaps between the tiles that overlap and find models that describe how those should be oriented relative to each other. And then we solve a system that tells us the optimal location and deformation of each of those tiles in 3D space. So, but let's go back to the collaborative development. How does this all start? So the Allen contacted me, they had these gigantic data sets, right? Really 50 terabytes per channel, and in need to be able to stitch those things together. This was a real showstopper at this point. We had software that I had developed back in Berlin, and it was kind of a bit on the shelves, was used in Fiji, but not ready to be scaled to the kind of next level. It was a useful piece of software called Big Stitcher, allows you to interactively align those samples. It's built on powerful libraries like ImageLib, ZAR for storing the data, N5 and HDF5, where you store the data in a multi-resolution format, meaning like in the Google Maps sense, you can load just a piece of the data that you need at the resolution that you need it. So this was there, but it didn't work, right? Because we didn't even get the software really to the... I couldn't improve the software because I didn't have the data. So, of course, the first idea is, okay, let's ship tons of hard drives over and get started, right? But the time was ripe to say, no, that's not how we're going to do it. Instead, the Allen Institute, what they did, they partnered up with AWS, Amazon Web Services, and they used the key source S3 storage. So what they did is basically uploaded all the data into the cloud. We did not send hard drive. I could interactively access all this data, right? On my notebook, I can load this 50 terabytes of data as in the video I just showed you. And I could develop the code for, first of all, just accessing this data and at least allow local processing of it. So all I did in the beginning with my group was to basically add S3 support and other cloud support. which at least enabled us to be able to look at the data, to process it using Big Stitcher. But we had a big problem that it was still limited to multi-threaded processing. So it wouldn't scale to the size of data that we need to process. So at this point, we started developing Big Stitcher Spark, which is the same functionality available in Big Stitcher and Big Stitcher Spark. So the cool thing is you can look at this in the GUI, like this, and you can at the same time, each processing step do in parallel on the cloud, locally or multi-threaded. And we added tons of functionality to the old Big Stitcher version to kind of support this new type of data. One thing I want to point out is one advantage of this Big Stitcher Spark module is already that it is command line based, and it's much easier to write your own code for this functionality, for this repository, simply because it's not GUI based code, but it's command line based code. It means it's easier to read and easier to work with. And I can just, if anybody's interested in this, I'm regularly now using Claude Code as my coding helper, which is an amazing thing, right? You don't even need to know a specific language anymore in order to extend code. It's just something that I have been growing pretty fond of. Anyhow, with this Big Stitcher Spark being written, we now could bring the data and the compute to the cloud using, in this case, serverless EMR, which is the service that we use to run Big Stitcher Spark on the data. And everything was basically running smoothly. This is just to give you an idea of the type of processing that we do. We define the data set, we resave it into OMESAR that we support now, we find the interest points, we match them, we solve the whole system, we split the data set into small pieces, and then fuse this into one coherent output volume. And everything was implemented by just using the data that is on the cloud. I never downloaded any of it. That was pretty cool, I thought. So, for example, just for compute, this is how we did it. We used AWS EMR. All you do is basically upload your compiled code together with the parameters and run this. And we could run this for interest point detection, matching, optimization, and fusion. And the cool thing is this EMR basically scales up with the demand that you have. It looks, okay, there are 10,000 little work units. Okay, so I will get you 3,000 CPUs. That is a good deal. And the whole thing is done in an hour. It comes at a price, but it's a pretty neat way how to do compute. This is how this looks in practice, right? You have your EMR website, and you get all these previews, and then you can actually look at the data. So it's a very intuitive process. Meanwhile, we further improved all of this, right, with the data that I showed you at first. So now we also have intensity correction, we have non-rigid fusion. So tons of things that I think can also be very relevant for when you build up your Lightsheet network in South America, I hope. Since I have a bit of time, I wanted to show you just a few of these steps in detail to get a bit of an understanding of how these things work under the hood. And I just wanted to focus on the alignment part, right? So you have many of these images that we want to just find out how they're oriented relative to each other. So here you saw an interactive rendering of two of these overlapping images, and we find these corresponding points here highlighted in red. And these corresponding points basically tell us how these two stacks are oriented relative to each other. But we have this for all overlapping images. And with that, we can solve a global optimization problem that minimizes the distance between all corresponding points, which ultimately puts all the stacks in the correct position that you then can use as a recipe to fuse your data. Usually we end up with errors around a few pixels, so it's usually a pretty neat quality. Another nice thing is that Big Stitcher allows you sometimes, in case the alignment did not work, which can happen, to go in there manually and just fix things, right? So you can go from the command line where you run all these things back to the user interface and say, my goodness me, I spent so much time or money into the sample, I just want this to be aligned. You do have the manual tools to actually help the alignment. Once this is done, we figured out that often the alignment quality is not sufficient because the images are sometimes too big to be efficiently transformed by a single affine transformation that we usually do. So what we did is we developed code to virtually split each of those images into smaller images, which then significantly increases the alignment quality of the data set. With that little tool, we were able to finally solve, to align most of the data sets with sufficient reconstruction to trace all the neurons through these data sets. And the last thing that we added was intensity correction. That's also a very important step. So often you acquire your data and they just don't look alike. They have different intensity levels, they have shading issues. So we do a set of tools to kind of make the images really nicely uniform. Here you see a Z layer 10 and a Z layer 300 in such a stack. You see these patterns, right? And here you see it kind of gets darker towards the top. So we estimate a dark field and we estimate a flat field using BASIC or Cedral, which are all established tools that one can use, and then fix everything. Now the dark field looks like an empty image looks like an empty image, and an image with content, you see that now it's nice and uniformly illuminated. It is still not sufficient, so what we do on top of this is we take each image and split it into little coefficients, where each part of the image is independently corrected for intensity. What we do is we set things up in a way that within one image, the coefficients that are next to each other should be rather similar. And for images that overlap with each other, we say that the pixels that are in the same location should have the same intensity. This again gives you a system of equations that we can solve globally, same as with the transformations, that ultimately gives you a nicely homogeneous output image. And this is the type of data that you actually want to work with. Then we can fuse all of this into one coherent image, and we recently improved this performance significantly in order to be able to work with large volumes. I'm currently adding non-rigid deformation for some samples that actually do experience that, and you can save this in modern formats like OMESR or also 2D, but just in case somebody needs that. In the end, you get these images reconstructed, and this is how this looks like. I hope the video somehow gets across again. So this is a 85 terabyte sample of a mouse cortex, 16 times expanded and imaged a Philips Keller scope. So you can zoom in, and this was actually also stained with synapse stains, so you can see where the neurons connect. And it's really an amazing resolution that we get, right? Each of these little fibers is a neuron, and we can now use those kind of data to try to attempt connectomics using light microscopy, which is one of the things moving forward to hopefully actually understand how the brain works. So the movie will zoom in still a bit more at another piece for you to get a feeling for the type of data that can be acquired with light microscopy and the tools that allow you to reconstruct it at that level. So I wanted to summarize this part a bit, right? So I think the collaborative development was really key for just getting this project off the ground. The AWS services enabled us to efficiently develop this Big Stitcher Spark reconstruction pipeline for petascale microscopy. In general, I think there's lots of potential for processing data shared on the cloud, and I will show you another project in EM that highlights this post-processing even more. Because right now, we are at a point where we can reconstruct the image. Now the next step is segmenting all the neurons, proofreading all the neurons, and actually doing biology with it. And in the M world, we are a bit further along those lines, but here we are kind of catching up now. And again, I think it's an amazing mode for working with people, with groups across the world on data. I don't even think it matters much if it's big or small. And just on the Big Stitcher part, so we have this pipeline. You can run this locally on the cluster or on cloud. The data can be local or on the cloud. And you have a user and developer-friendly integration of GUI-based and command-line-based processing. It's all open source and builds on powerful libraries. And most importantly, it also works on small data sets, right? I mean, it scales to large ones, but it also works on small. Okay, the last 10 minutes, I want to talk a bit about the other thing, electron microscopy, right? And the parallels are, I think, obvious, right? In our case, it's both about connectomics, but you can look at so many other things with EM as well, right? So what we wanted to do is to create the connectome, the map of neural connections in the brain, looking specifically at the mouse, at the Drosophila. It was actually recently published, so this bioarchive is pretty new, the complete connectome of the Drosophila male central nervous system. And this is an even more collaborative effort. And I think the light sheet is going to go exactly in the same direction, right? You have sample prep, imaging, alignment, then you segment the sample, you do segment the synapses. In light you can stain them, in the EM you actually have to find them, then you do proofreading, this is a circular setup, and then you do analysis of the data. Just to give you a bit of a feeling how this looks like, this technology, this is very sensitive and brittle. You can do one sample or two, right? So this is kind of not like light sheet microscopy that can scale to hundreds of samples. This is somebody like Kenneth Hayworth took years to develop this, right? They take the Drosophila brain, chop it into little sections, and then image them with focused ion beam microscopy. We have 8 of them. We bought, each of them costs a lot of money. It's a destructive technology. You image one Z layer, it's gone. So you really mill yourself to the sample. So anything that goes wrong in the imaging process means you have to start over again. So tons of issues, but we got a few samples out, which is pretty amazing. But again, I wanted to show you how this works globally, right? So we do this sample prep, imaging and alignment at Janelia. This sample is then used by Google in Zurich to do the segmentation. Then proofreaders in Janelia proofread these segmentations and go back and forth and back and forth. And at the same time, we also do the synapse detection. Once this is in a state that it works, Cambridge University in Janelia mostly analyze the data, but it's worldwide accessible. Anybody can look at this data and can work with this data. In this case, we use the Google stack, not the Amazon stack. It's all based on Google storage, Google Data Proc, Bigtable, BigQuery, all the things that Google developed for the cloud services. So again, I wanted to show you a little bit about how we did the alignment, just to get a bit of an understanding of the scale of that. So it took 18 months with 8 of these microscopes to acquire this data set, 7.5 million images, 845 terabytes in raw data, 66 of these slabs that creates a final output volume of almost a petavoxel at 8 by 8 by 8 nanometer isotopic resolution. And what's really exciting about it from a computational aspect is that anything that can possibly go wrong does go wrong, right? Because even an algorithm that works 99.99% correct will still fail almost 1,000 times on this data set. So the big challenge here was, how do you get it done right and in time? When do you try to developing and improving your algorithm? When do you write interactive tools to just fix this by hand and spend a week or 2 by hand to fix things as much as you can? This is how the pipeline looks like. You'd have 66 of those slabs. You have to align them. You correct the milling depth. You find again these surfaces because they were re-embedded in some resin, and then you put them together into one volume. Just quickly, the stitching works the same as in the light sheet. You find overlapping points between pairs of images, and that you can use to align this. But ultimately, you have a big system of overlapping points. Thousands of slices that are then connected in Z, plus minus 6 slices, 100 million correspondences. Huge problem. So we use the same solver that we used for light sheet, but now we actually had to improve that solver that it can be distributed. So we wrote a distributed version of that solver that breaks the problem into small blocks that are then later combined into one seamless output volume. This development really actually made this project work. It was stuck at a point where people just couldn't do the alignment. This is again distributed on Spark in the cloud or on our cluster. And this is how the same thing looks in Google Cloud. Again, you just upload your code together with the parameters, run it, it scales to the size that you need. Pretty neat. But again, this works local or with cloud. So once you have these all reconstructed, you have to re-detect the slab surfaces. So here you see one of these EM slabs from the side. Dagmar Keinmüller defined this handcrafted cost function, kind to estimate where it starts and where it ends. Together with Jan Funke, we also did a machine learning-based classifier for the same thing. This is both error-prone, and we use a graph cut to find the most likely surface that then allows us to straighten this out. This is again one of those things that works in most cases, but in many it just can't, because even as a human you really don't know where to put the surface. Here you can't see the surface. So what we did is to write interactive tools that allow you to go in there, load this 5 terabyte volume, again you have 66 of those, go in there and try to fix these transformations by hand. Right? So you load that volume, you find an area that is wrong, and you can just fix it. And again, if the stuff is in the cloud, anybody can access this data and do these types of transformations. Once we found the 66, so this was 1 to 2 months of my manual curation at the end, was to align those slabs together. This is multi-pass alignment that continuously refines these surfaces, trying to match them together. And it's again one of the things that works in many cases and others not. And we wrote with Tobias, again, a tool that allows us to manually change these surfaces so you can match them by hand in cases where the automatic alignment fails. And again, this is the direction that light shield microscopy now goes as well. You will eventually cut these mouse sections into mouse brain into much bigger sections that we then need to align exactly the same way. The last thing we did was to combine two gigantic volumes. We had the volume of the brain and the volume of the VNC, each of them, a few hundred terabytes. We defined a transformation for the neck that allowed us to interactively transform this gigantic volume and simply attach the VNC. So we deformed this a little bit to then exactly match the other volume, which allowed us to create this gigantic, almost 1 petabyte volume of the Drosophila brain. So this data set is then sent to Google, and actually if you process it on the cloud, it's not even sent to Google, it's just there. All that Michal does then is run his flood-filling, pre-trained flood-filling network to segment those neurons, which is then, again, proofread by a team of about 25 proofreaders who just access the same data that sits on Google servers. And ultimately, after many, many iterations of that, this is what you get, a finally aligned and segmented volume of the entire Drosophila central nervous system. I have some still renderings here, just in case the video didn't look so good. So this is really a quite impressive piece. So I wanted to use the last 4 minutes to discuss some final thoughts on all of this. So I wanted to show you is that these large projects don't even work without distributing data. It's essential. Without that, you just couldn't do it, right? Sometimes you even need to distribute the compute as well. And it is an amazing mode for working across the world, right? We work with Google, we work with the Allen, we work with Cambridge, we work with many others. Just by sharing this data centrally, giving a common goal, like we want to do the connectome, and then people ship in and you can have these gigantic, nice projects where you create communities. And I think this mode of working is just, could be a prototype for, I think, science in general should be done. Right? Because you shouldn't do this on your local computer anymore. Data should be shared. You should work either with the entire community or with your set of collaborators. You should all look at the same data, and all of this is possible now, right? The cloud offers tons of potential for exactly that, right? For sharing the data, no shipping of hard drives around anymore, right? You only share the parts of the data at a resolution that you actually need. So in some sense, these large data sets, you don't ever look at all of it, right? You look at whatever you need to reconstruct your 5 neurons of interest at the biology lab. Or for me, I use a downsampled version to align the data, and so on and so on. You can do collaborative analysis, right? You can quickly iterate results between many groups in different locations. You can discuss the science looking at the same data and analysis. For example, a neuroglancer, and I want to show you just how this looks for this data set, right? So here's a neuroglancer view of an earlier version of that data set, still a few 50 terabytes. The entire volume is here. You can look at the segmentations together, right? You can zoom in. You can select those neurons, you can work with them, you can do 3D renderings, you can run analysis on this. So all of this code that you write locally and run locally with data that is centrally accessible. Yes, and I think another thing is about the collaborative development, right, that we did for the Big Stitcher Spark. You can develop software and pipelines together with many groups around the world, or you can divvy up, you do this part, I do that part, as long as the data is in a central place that everybody can work with. You say, oh, I got this new result here, can't you just build your analysis now on this? So I think this is just a really cool way how to do this. And another plus is that you can easily get advice from respective experts in the field. You send this NeuroGlancer link over and say, hey, this is what I did. What do you think? Could we do this better? What are your thoughts on this kind of cool organelle I saw here, and so on and so on. So in summary, I think shared data allows us to create shared challenges, which then create community, right? I don't think just sharing data alone is enough, right? You need somebody who coordinates this, who says these are the data sets that are there, these are the things that we want to achieve, who wants to chime in, right? There's so many people that are good at what they do, especially in the computational sciences. All they lack is sometimes data and a goal, right? So I think this is really something that one can achieve if one goes that route. And shared challenges are arguably one of the most powerful forces in community building. They create something that's hard to manufacture artificially, genuine interdependence and shared identity. This is how Claude yesterday summarized it. I thought was a pretty good summary. And I think if you go that way, right, I think there's a big opportunity there to do it. Of course, this comes at a cost, right? Local storage, you pay once, cloud storage costs monthly. It does, but you should make the math considering a few things. Local storage has a huge opportunity cost because the data that you acquire at a huge cost may just not be effectively used. Somebody uses in their lab, it's way below its actual potential. It's fully backed up, it's not tied to individual people and their career choices. And local storage, as I tried to point out, has very limited opportunity for collaborative work. Cloud storage may even be free if it's open access. There's the AWS Open Data Program. I talked to them already. I know you talked to CCI. Google may also be interested in supporting such initiatives where you say, okay, we're going to make all our data open and everybody can work on it. Distributed computing is still a different topic. It's very expensive and may make sense if a certain hardware is required or to get results earlier. But I think one important thing we learned is always write your code in a way that you can easily run it distributed if you need to. Use frameworks like Flask and Spark to be future-proof. We paid a huge cost by not doing this in the beginning. It's just something to consider. Okay, last slide I wanted to point out, we have this gigantic initiative at Janelia, also where we now injecting AI system into every stage of the scientific process, just in case you're interested. And I want to thank a lot of people that contributed to this. And yeah, thanks so much for listening. And if there are questions, I would be happy to discuss.
Thank you, Stephan. Fantastic talk.
So I have two questions. So you mentioned intensive use of the cloud services. So how much is the cost, for instance, to merge and process this 50 terabyte stack, taking into account the transport, I mean the transfer of the files, the processing, everything? And the second question, you show some interactive 3D rendering online. So what kind of connection does that need? Something special, or like 1 gigabit, 10 gigabits, 100 gigabits kind of connection? Thanks.
I'm going to start with the first one. I didn't really get the second one yet, but we can get to that after. So we have it all set up that we don't pay for cloud storage. Right, so Google pays for the FlyAmp project and for the Lightsheet project. We're doing it locally right now, or the Allen Institute pays. And it is a substantial cost. I actually don't know the storage cost, but you can look it up. It depends on the storage tier that you choose. The compute cost is similar to the compute cost of a local cluster, at least for us. So I would have to remember how much you pay per, it's a few cents per CPU per hour. It's not a gigantic cost, right? I think the biggest cost usually comes from, if you don't do local compute, comes from the storage. So the storage is a few dollars per terabyte per month, which one can pay. But as I said, we usually try to strive for getting this for free. And I think as a scientific course, there's a good way to go there. right? There's all these open data programs where you kind of don't pay for this at all. But basically, each of these cloud providers, so where we pay, we pay for our backups. Our guy Goran, he always tries to find the best deal. Sometimes it's Oracle, sometimes it's AWS, sometimes it's Google, and yeah, then you pay a few dollars per terabyte, per gigabyte per month. So that's basically the average cost. I'm not sure if this really answers the question. And the compute also depends on, you have thousands of different things to choose from. CPU compute is affordable, GPU is very expensive, for example. So we often also make the math, do we need local compute, do we need central compute? And we usually use a mix of the two, where we do locally what we can do locally, and only when the project actually requires us to run this at a scale that we can't do locally, we buy these services. So we often are in a mode where we buy most, what we do pay for is the storage and not the compute, if we can. And does this answer the question?
Yes, more or less. About the second question, you remember what do you need in terms of connectivity to do interactive 3D rendering?
Not much. I mean, I run this here on my notebook from home, right? So I do have a gigabit connection, but it's pretty good. I mean, at least throughout COVID, I think most of the countries improved their internet connections pretty substantially. So even when I visit people in Europe or in South America, usually that like a normal internet connection is sufficient for that, right? The point always being that you never download it all, right? You always just download the few things that you need, for the rendering or the compute that you need to do right now. So I think it only becomes a problem if you need all the data. Then bandwidth is a problem, but for most computes and visualizations, it's completely fine to be on a low bandwidth connection.
Okay, thanks.
Any other question? I do have a question, well, more a comment or reflection. What you share as a model, right? The AWS or the Google. So there are several angles that I think will be interesting to explore for Latin America. Well, the first thing that you mentioned is, well, when you share challenge, well, you can put together a community, right? And I think this is all about Lavi, right? Lavi can be, you know, I believe is in the position to coordinate, such as Ford, and organize an initiative that can spoke with AWS. We already spoke with you about this possibility, and I think there are opportunities for Amazon to share, you know, at least for some time, to start with some experience on using the cloud for storage, but also for all the analysis. And the other thing that I believe could be very interesting is related to the, well, first of all, you know, of course, always there is scarcity in resources in the region. There will be very hard for, you know, having a hub, one place where we can deposit all Latin American data and then shareable. This will be a big responsibility, even for the big countries in Latin America. But on the other hand, we have other scarcities, not only money. In my opinion, one which is very important is also the critical mass, right? And you share, you know, your expertise in collaborating across the globe. And I am thinking not only in Latin America, across America, where we can have you for sure, you have been already very humble to offer, you know, your support and help in implementing such a thing, to collaborate in initiative that require this terabyte scale data analysis, right? So how you consider we can approach such a thing, you know, for establish something to begin with, AWS or Google Scholar? What is a priori your first choice, Stephan?
I mean, I think in the end, which provider one chooses doesn't really matter so much. I think what matters more is what is the common goal, right? What is the challenge that one would set up? For example, if you say, we're gonna, for example, let's take this light sheet stuff, right? You get 3 scopes and you say every data that is acquired on there should have some aspect of a continent-wide challenge, maybe, right? Like, for example, this data set, we want to find all nuclei. This data set, we want to find all neurons. This data set, and kind of make the challenge available to many people, right?
Correct.
We had a lot of issues that this wouldn't go well with the egos of many labs saying that I need to solve this, I want to solve this. But at the end, this is much slower than if you actually get a kind of community together that tries to solve a problem, you know, as a whole.
Yeah.
So I think I would start thinking about challenges to set up first, and I think we would definitely find providers that would likely host this for free. Right? For example, we made an CellMap challenge that I should have maybe shared a link about, where it's about enabling people to write the best AI-based segmentation tool for cell organelles, or something like this, right? Another thing that one could do is, like, whenever you use microscopes that are publicly available, like you have to make the data open. Right?
Okay.
Because people are always afraid that somebody's going to steal something, but in practice, I think that rarely happens. What is much, much more likely to happen is that you find a new collaborator that works with you on your project.
Yeah.
So maybe those 2 things together, right? Just
I like your perspective.
change it. I'm happy to help with the technical implementation of this, right? Because in the cloud, there's a little, how do you load the data, how do you access the data? But all of this exists. I think thinking about why and how to do this, specifically why, is the more important thing. And
Yeah.
I think it's a brainstorming that one would need to do, right? Like, how do you convince people that this is a good idea? And how do you get people to participate?
I like your perspective, and I think we have a first choose or eventually a one good candidate for a shared, problem, which is named flamingos. So I think we have something there. So there is another question here.
Hi, Stephan. Thank you so much for your talk. Kilder Miranda here from the Federal University of Rio de Janeiro. So just a follow-up question regarding our Latin America infrastructure and critical mass, as Leonel just said. Is there a roadmap or a strategic way of mapping our strengths and weaknesses so that we can have a good map of our situation and then start with a program or something that could lead us to organize as a group, as a network that could benefit from this big data analysis and management?
I mean, I feel it's really more a question for Lionel than for me, because I don't know that. I think it's a good idea to do this, but I'm not in a position to really answer this question, I think.
Yeah, I think it's a homework that we have to do. Well, we are on time for next session, so I want to thank you one more time, Stephan, for your generosity to be participating in the LAVI meeting, sharing your expertise and experience handling with a massive amount of data. And I hope we can have you soon back in Latin America to continue our discussion. Thank you.
I hope so too. Thank you so much. Sorry again for not making it this time.